So I have a significant amount of content, so I'll try to go relatively quickly. If you have questions about specific things, just hit me up in Slack. And my talk is, or presentation is a discussion of security hardening with OpenEmbedded and Yocto project. The agenda is basically a sort of a description of security hardening and what we mean and why it's interesting these days. Some discussion of basic hardening for security with OpenEmbedded and Yocto. And then I'm going to run through a description of what tools are available and in some of the various layers. So some caveats up front. I am not what I would consider a security expert. This presentation is sort of driven by an interest recently to sort of get a better grasp of what different tools are available and support for different security features is out there in the ecosystem. And it's definitely not exhaustive. I'll mention later on, there's a few things I haven't mentioned about some of the layers that I haven't covered. And as well, just to have this sort of upfront, your security requirements for your product are going to be, highly dependent on how secure you think you are, what your threat model is. And this presentation is purely just to show what are the tools that are sort of available in commonly used layers. So what do we mean by security hardening? Hopefully that's not a new phrase to most of the people listening in. But basically, we're talking about securing a system by reducing its attack surface or the sort of available things that could be vulnerable. So usually this means removing unnecessary software or services, unused users that might be available for attackers. Potentially, we're controlling network access, so firewalling off various things that shouldn't necessarily be accessible. Might include intrusion detection, which is there's tools to sort of detect whether files have been changed, things like that, as well as improving general things like the password behavior of the product, and of course the classic thing that's always discussed usually in Dev Day is like long-term support and maintenance for removing vulnerabilities by upgrading software. So that's what security hardening is. Why are we, in need of this these days? Basically, it's the classic story of everything is becoming connected to the internet, the classic Internet of Things that sort of popped up 10 years ago. And of course, attackers are now becoming more aware of Linux devices exposed on the internet. There's commercial services even that regularly scan all of the IPv4 address range looking for devices and scanning them. But I have seen, there's papers published where, grad students do this just to sort of measure the ecosystem. So it's not something that's unusual. Things will be found if they're on the internet and vulnerable. And of course, customers can't usually be relied upon not to attach devices to the internet. This is a classic issue of that things like showed and expose, or people plugging things directly into the internet. And in the past couple of years, there's been some visible incidents where universal plug and play has exposed things behind firewalls to the internet that people just did not expect would be a problem. And there's actually been some things recently around denial of service attacks coming from that. And speaking of that, the attacks might not be direct. It might be someone using your device as part of a distributed denial of service attack. And so that's generally not something that you want to end up in the press for these days. So it turned out this weekend during ELC, there were a couple of discussions with a lot more detail about sort of the security for embedded Linux. So I have links to them here in the slide deck. The first one has a discussion of how you would determine your own, threat model and what you're concerned about, and determining how much security you would like. So that's kind of useful information. I'm not going to go into much more in depth necessarily on that. But I will mention this. A couple of presentations I saw this week mentioned the OWASP IoT top 10 vulnerabilities list. So OWASP is had been started as a web application security sort of consortium or group. But back, I think 2014, they started doing surveys to determine Internet of Things top 10 vulnerabilities. And the last survey that's available at the moment is the 2018. I believe there's one in progress right now. And so that's available at the link that's given there. And as well, they actually, because OWASP is a web organization, they actually have a top 10 for web app vulnerabilities that could be useful if you, I mean, there's a lot of devices have web interfaces now. So that's kind of a useful thing to have as well, potentially. So here's the list. I'm not going to go too in depth into them, but we'll see that, I mean, the top few are things that we do typically end up discussing around OpenEmbedded and Yocto. I mean, weak, guessable, or hard-coded passwords, that's a pretty classic thing that a lot of embedded Linux security issues have been sort of pointed to over the years. People shipping devices with, root or admin passwords and, not having a mechanism to force customers to change them. The second one, insecure network services, is things like FTP or rlogin, RSH. Those are, because they're not encrypted and tend to, I mean, some of them don't actually even have passwords, but they were pretty common in network devices back, 10, 15 years ago. And if you're still using things like that, it's less than ideal these days. They're too easy to hack. The third one, ecosystem interfaces, refers to accessing cloud services or servers without proper security. So things like SSL and other types of mechanisms to ensure authentication and encryption of your communications off a device. I'm not really going to talk too much about that particular thing. That's a kind of a more generic issue around the ecosystem. Lack of a secure update mechanism. And that's, if you actually go look at the OWASP document, they give detail on what they mean by some of these things in more detail. And so this includes like having that your over-the-air upgrades are actually encrypted and can't be spoofed and things like that. So they actually go beyond just having that you're updating the software to fix vulnerabilities. They want that to be a secure mechanism. And that leads into the insecure and outdated components. I mean, that's the classic thing that, we always discuss around building our own distros. And then they start to get into things that are a little more abstract from our perspective. Insufficient privacy protection is more of, not having user supplied information encrypted on a device. And meeting some of your, maybe you have GDPR or other similar standards, things like that. Insecure data transfer and storage is similar, is related to that, as you might actually, if you have a device where you're really concerned about physical security, some of these things start to get more difficult to achieve, right? You actually have to have encrypted file systems and things like that. And so device management is a more interesting one, because in the bigger, more commercial security community, things like actually device tracking become a lot more important. Generally in embedded Linux, I've not seen a huge focus on this, but being able to actually know where devices are and actually know their status and things like that is quite important in a bigger deployment scenario. And the last two, I think, are relatively self-evident. Not actually testing your default settings and having things turned on that shouldn't be, that type of thing. And of course, physical hardening, which I've outside the scope of this discussion. So those are the classic ones. People surveyed said these are the things that they've seen as being big issues. So what can we do? I mean, we're using Yocto to build our own embedded Linux systems. What can we address in those 10 vulnerabilities, or at least the top 5 or 6, let's say, with what we have in our toolkit? So the manual, actually, if you go look in the development manual, there is a section on making images more secure. It has some useful high-level guidelines, with some of which are sort of directly applicable to some of the classic vulnerabilities like passwords and things like that. It talks about disabling some of the debug features that might be on by default, and how users and passwords would normally be added into an image, and a discussion of security-related compile flags. So there's the information there. And it mentions the meta-security and meta-selinux layers. And it's useful. There's good information there, but it's somewhat a starting point, basically. You need to, I mean, you're not going to build a secure system necessarily with just what's in that section of the manual. So expanding on what's there, just with sort of, things that I'm aware of to do with, just with the base Yocto system, or you definitely sort of address some of the things with having too much in your image that increases your attack surface. Check your image manifests, looking for things that you don't expect to be there, and then go back and figure out how to remove them from your images. The OE package data utility is useful for figuring out what package a file in an image came from, and that gives you somewhere to work backwards from, potentially, if you're actually looking at your image and seeing files you don't know where they came from. Distro features is another option. Things in distro features can go through and pull in package groups. So if you're basing off of Pocky, it definitely by default includes a lot of things that you might not actually want, like NFS and Bluetooth, and depending on the device, the pulse audio and things like that. Some of these aren't necessarily going to be particularly vulnerable, but I mean, you don't really want to have all this extra stuff in your device and ask for trouble. And I'll just reiterate, it's mentioned in the manual, but the debug tweaks image feature is on by default in Pocky, and that's what clears out the root password to make it convenient for development. I mean, it's probably most people are going to be aware of this, but you don't want to ship that with that, of course. But in my mind, you probably don't really want to actually regularly build with it turned on. You want to get used to having a product-like image with a more product-like user system. So whatever scheme you would actually ship for your root user or admin user passwords, actually test with that, and only really use like the debug tweaks or similar feature purely for development, or potentially QA builds or something. So another thing that is pretty typical would be to review the kernel configuration. So you go through, I mean, there's a security option menu in the kernel config, but there's other things around in the kernel configuration, like hardware random number generator support, which has become important for certain things these days. The architecture specific address space randomization features are actually in the architecture selections. So that's the basically shifting things around at boot time to make it harder for rootkits to function, basically. That's the kind of support you get from that. I'm not going to go into huge detail. There's a few guides around on the internet. I've linked this one here. They actually have a patch kernel, but they do discuss why they configure certain things in their kernel configuration, certain ways for particular types of hardening. So that's maybe a good starting point if you've not really done this before. And I'll point out that it has been pretty classic in embedded Linux to use the devmem device, so config devmem option, to basically work around driver issues or lack of drivers, but basically directly accessing memory map registers with the devmem or devmem2 utilities. And realistically, these days, you should hopefully not require that anymore. Hopefully you have drivers for things these days, or can find someone to give you a driver. And so it is a bit better. They have made it more secure by default, but typically the hacks that people do require turning those options off to make it work. And it's really not good from a security perspective. So I'd like to reiterate that you do not, these days you do not want to be using config devmem. So to continue on the kernel sort of track, so BSP layers, it's pretty common that they don't necessarily enable desirable features. So things related to C group and namespaces and a lot of the, netfilter options might not be enabled. And these days it's maybe typical they won't necessarily have all the BPF options turned on if you're starting to get into using that. And these things become a little more visible when you're using systemd or some of the container runtimes. And Robert showed earlier in his talk where he was running this Docker, I think, config check, which goes and looks at the proc config.z, I think, to work out what options we're on. So it'll tell you whether it's missing stuff. But systemd will tell you at startup, actually. If you look in the journal, it actually will say if this feature is missing. And so there's definitely BSPs out there, commonly used ones, that you will need to add some config options to make systemd and some of the other things like Docker happy. And then there's the corollary of that BSPs might actually turn on a lot of things you don't want. They tend to be geared towards having a broad spread of drivers on for, people building demo images and stuff like that. And realistically speaking, you really want to pare that down. You don't want random like USB drivers for, various odd devices in there, because those are the kinds of things that people might find a bug in and actually figure out that they can trigger plugging in something that will, exploit it. So it's kind of try and pare that type of thing down and just have the, kernel as small as possible. And as well, I've seen there's BSPs that turn on a lot of debug options by default that, it's not great for performance sometimes, but it's also, they might be exposing things that aren't necessarily things that you'd want visible to users. So the number one OWASP top 10 list one was user passwords. So as what's mentioned in the manual is a discussion of just actually like baking in a root password or a user's and a password at image creation time. But realistically, these days, a lot of devices aren't doing that, or at least they're having a device specific password. So I haven't seen any good examples of integrating such a thing or like a pre-built like class or tool to do that. So I assume most people are just building their own custom implementation. It'd be kind of nice to maybe have an example that showed that, because realistically speaking, these days you kind of need to have it in a product. One thing I did see is the past WDQC library has a recipe in meta-OE, and it's actually used in a lot of the desktop distros. It's something that you can configure to actually test password strength. So it might be an option if you do have an interface on your device for the user to set a password, to actually call into that to, configure it with some rules for how strong you think the password should be. One of the other options that's available in, OE core is root file system read only, which basically is what the variable suggests, where the root file system will be mounted read only on boot. I think it's worth considering for products if that's something that works with your product design. It definitely increases difficulty for attackers, especially if you have capabilities set up for things such that getting mount privilege is very difficult. And also has a secondary benefit of allowing implementing reset to factory default. That's becoming a little more common, that people will use a read-only root file system with overlay FS or similar like links into writable partition types of things, because it's very straightforward. With overlay FS, you can just throw away the overlay and you're back to your factory defaults. So there's kind of a nice benefit of getting that working. But that said, you might actually need to do some development. Your locally developed applications might expect to be able to go right out into Etsy or things like that. And there might be other packages outside of OE core that might not actually expect read-only rootfs from to be there. So you might have to, if you're using recipes from some other layers, you might have to do some tweaking to make things work. The other thing to note, and because it came up there was a discussion the other day about this, but the combining with mandatory access control, and SE-Linux would be the example because it has to label the file system. Making that work with read-only rootfs is probably going to take some development. All right, let's check my time here. 10 minutes. I'll have to go faster. Back to the other, sort of outdated software thing. I mean, it has been discussed in previous dev days, and I've seen talks at ELC. I mean, the big sort of thing is security issues, which are like CVEs. And so there's actually surprisingly not a documentation on this in the Yocto manuals that I could see beyond just the basic indication the class exists. But CVE check, basically you can inherit that in your like local.conf and then do package or image builds, and it produces some data on what CVEs the packages may be vulnerable to. Uses the NVDCV database. So there are some data dependency issues there around accuracy and completeness. So you will have to probably do some research yourself if you're actually, want to vet the security of your products. But it is a handy tool. I found you're probably going to have to process the output if you're using it in your own workflow to like drive maintenance and become aware of CVEs potentially being an issue. And the other thing that's you should note is, at least when you run it on stock images now, there are some CVEs that aren't whitelisted, and my guess is because it's there's some package configuration related things where you have to decide whether you consider to be okay that the CVE hasn't been patched, because some of the CVE write-ups are very generic and say this package is always vulnerable, but it's specific use cases with specific configurations that don't necessarily apply to OpenEmbedded. So if you're getting into this workflow, you'll probably have to do a little bit of research on some of these things and decide whether to whitelist them or not. And I'll throw a pitch in here for SR tool, which David has kindly developed over the last couple of years, which is basically a tool to allow you to do CVE issue tracking and build up your own workflow for that. So I'll try and get through as much of this as possible. So meta-security is the big sort of toolbox here. It's maintained by Armin Kuster, who just was talking about the bug tracking. And it has a set of recipes for variety of things, everything from just libraries through compliance solutions, some support for secure boot, and integrity or attestation, which is checking the device file system integrity, some intrusion detection support and scanners, and of course some MAC support. There is a documentation file that describes some of the big packages that you can look at. And so I'll quickly run through these. So I'll highlight libseccomp because it's something that's actually used in a variety of other packages. And it's actually worthwhile potentially, if you use systemd or any of the container runtimes, just include meta-security anyways to configure using seccomp with them, because the system call filtering that it provides, the kernel system call filter, you do see a lot more documentation these days talking about setting that up with systemd, and as well the container runtimes, you'll see a lot of default configs for them are expecting it to be there. And so that you just need to note that you probably will have to set the package config to add it in, somewhere in your build, maybe append or in local.conf. There's some other helpful libraries. The Google Authenticator is interesting. I've read some stuff recently where there's starting to be a bit of pressure. People are starting to want multi-factor authentication for embedded systems. And it's actually an interesting thing because on Linux, that's not, at least for outside the web, it's actually not something that's too commonly used. It's starting to become more interesting. So I'm curious to see if we're actually going to get a lot of pressure and there'll be more support required down the road. So compliance, there's a Linux tool, there's a link there. It's based, Linux and OpenSCAP are sort of can be considered as runtime auditing. They check system configuration and look for file permissions and things like that, look for set UID binaries. OpenSCAP is interesting. I think Armin can probably discuss it if you have questions in Slack, because the NIST have standards around basically standardized naming of packages to basically simplify tooling around security issue tracking. And so the tools mentioned here actually are wired up to actually go check NIST and look for vulnerabilities, but also have support for pulling in other databases. So Armin's done some work to actually wire up, I think, package name mapping so that some of these things will work against OpenEmbedded. I haven't looked in it too heavily, but if you are in the market for commercial tooling, I think this starts to become interesting. But there are definitely smaller embedded use cases. I don't think you'd run them on target. It might be more of a QA thing where you would set up an image and do some testing. Secure boot and integrity. So there's a meta TPM layer inside meta security that basically has trusted platform module support. So this is a TPM 1.3 2.0 tools, has hooks for Linux Yocto to basically pick up the configuration for the kernel for those, depending on the TPM and TPM2 machine features, had some sample images defined to actually include the tools and build a complete image, and gives you a good starting point if you're building a trusted boot image for like Intel, which tends to have TPM, or if you have a hardware TPM on your non-Intel platform. Provides a useful starting point. You probably will need custom development for things like doing runtime integrity checking, like attestation, and like key storage beyond just normal trusted boot. You'll have to start doing some development there. Note that for ARM system on chips, typically the trusted boot or secure boot is vendor specific, and hopefully the vendor BSP has any tools or kernel changes required for that. As well, the trusted firmware component that's typically used has sort of shifted into a more, I think, consortium mode. There's a trustedfirmware.org now, and this meta ARM layer that ARM has created to try and shift things to a sort of a single recipe, as opposed to everybody having a forked copy in their BSP layer. So that's a relatively recent thing that John Mason's been driving. And as well, things like key storage for and setting up keys for image encryption. That's usually a custom integration. That's typically not available directly out of a OE layer. Getting low on time here. So the next sort of step in that chain would be integrity measurement architecture, IMA, and then EVM. So these are relatively old at this point. I think they went into the kernel quite a long time ago, but basically allow you to extend trusted boot up into user space, the sort of measured boot process, and also provide appraisal so you can do remote attestation to make sure the device is still has integrity. In practice, it's quite unwieldy to actually get working. The meta integrity layer in meta security has some sample recipes to sort of actually build images. You're definitely going to want to read up on IMA before you start jumping in and using it. As well, I'll call out there's a meta integrity layer also in that repo up on GitHub that is an alternate implementation, and it has sort of a bit more mechanisms around there. Digging around and actually working out how to use meta secure core is probably a whole other talk, so I'll proceed on. And the other thing is DM Verity. There was recently support added. So it's also integrity management, but it's a block device based system where basically every block has a hash. And it's simpler to implement than IMA, and it comes out of the Android sort of development. And there's a class now to actually generate images with the required hash information for the final block, device image. And there's a sample configuration for BeagleBone Black to actually build an image that will boot up and be, trusted. And so the actual integration of that with your secure boot on the platform is still an integration thing, though, because you need to get the keys into the Verity process. So there's also intrusion detection support. I'm going to kind of skip over some of these. The classic one is Tripwire that people have heard of, but these other ones, there's actually network intrusion detection tooling, and as well, Samhain is a more configurable file system scanner. And then there's some older runtime scanners. So I'll let you look on the slides. I want to get to the discussion of Mac and the updaters before I completely run over time. So Meta Security has mandatory access control recipes. So AppArmor and SMACK and some of the, I think the tool that you require to use Tomoyo. SELinux is in the separate Meta SELinux layer. So just a quick run through these. So application profiles for AppArmor that you get when you build the defaults, like tooling, there's not a lot. There's not a lot of profiles. So if you're actually using AppArmor in a product, you're either gonna have to write a profile or go and look for one in like Ubuntu or Debian for a particular server. So that's something you have to keep in mind. And as well, the SMACK policies I think you get with the default build are probably insufficient for product. And generally people consider SMACK a lot easier to set up than SELinux. But the issue there is that the user space is quite small. I mean, realistically, Samsung with Tizen are the biggest user, and they don't really interact with the community. And AGL use it as I think the only other project I really know that uses it. So you might be a bit stuck if you're trying to find support. So that kind of makes SELinux or AppArmor maybe better choices if you're considering using Mac, just because they have larger user bases these days. So then I'll segue into meta-selinux, which is where you would get your SELinux support. It has the tools and package groups. It's maintained by Wind River and Siemens developers. It has recipes for the reference policy configured for different types of policy. Targeted, you might have seen on like a Red Hat or Fedora box. That's a pretty classic one because it's easier to configure than the full multi-level. One thing to note is at the moment in Dunfell and master, if you just grab meta-selinux and add it in and build an image, the image won't boot in enforcing mode, which is not ideal. Had a discussion yesterday, the day before with somebody. I think we'll try and get that fixed because it would be nice to have that sort of be testable right out of the box. So SELinux is considered to be difficult to actually write policies for, and like quite difficult. And it's very likely you'll need to write policies if you're implementing it. The reference policy includes things I was a bit surprised by default, but there's definitely a lot of things that it doesn't. So why would you consider this? I mean, it's typically kind of outside of the typical embedded use case, I think, for a lot of people. And of course, AppArmor and SMACK are easier than SELinux, at least potentially. But the thing these days is that, at least in the server world, it has kind of become a key component of container security. And last year's big CVE about container escape from runc was blocked by SELinux if you had it. And so that's kind of, now with containers becoming more important, that would probably be something to keep in mind. And of course, these days, because RHEL and CentOS and Fedora have used it for so long, it does have a reasonable community, and there are people from the server world that actually understand policies. So I kind of think that probably makes it a very viable choice as a Mac system.
Okay, we're going to need to move on, Scott.
Yeah. So just the updaters, I just run through 4 updaters if you want to go through the slides. And meta-SCA is quite handy if you're looking for static analysis tools. Just make a shout out for that. So I definitely overestimated how much I could get through in 30 minutes. My apologies. If you have any questions, the slide deck is up on the wiki and you can go through and ask me on Slack. So that was a very quick and rushed, non-exhaustive survey of tools that are available. I didn't really discuss networking tools. There are a few in meta-security, and there's a few other odds and ends I have skipped. If I've missed something particularly useful, or if you would be interested in a focused follow-up presentation on a specific thing, just give me a heads up. My contact info is here, and I'm also on the Freenode IRC, the OE, and Yocto channels. So thank you very much.